Welcome back, math friends. This is AP Calculus, section 3.5, day 1 notes. We're going to continue talking about differentiating today. So far, we've learned how to differentiate polynomials, products, quotients, natural exponential functions with a base other than e, and recently our trig functions. But what if our function is a composite function or a function within a function? Remember, in our previous set of notes, we had talked about trying to differentiate secant squared x. That is a composite function because the inner function is the secant and the outer function is that something is being squared. So we need a new rule. We somehow need a way to differentiate a function within a function. And that new rule is called the chain rule. The formal definition says that if g is differentiable at x and f is differentiable at g of x, then the composite function f of g of x is differentiable at x and f prime is given by the product f prime of x is equal to little f prime of g of x times g prime of x. Well, what that basically says in layman's terms is that we differentiate the outer function f at the inner function g of x, and then we multiply by the derivative of the inner function. And I think as we practice this, this will begin to make more sense for us. So let's take a look at example 1. Our first job here is going to be to try to figure out what is our outer function and what is our inner function. And once we figure that out, we'll be able to proceed. That's always going to be your first step when you're doing the chain rule. So when I look at this function, y equals, and then I have a polynomial that is raised to the 4th power. So it looks to me like my outer function is that something is being raised to the 4th power. And whenever we talk about chain rule, we always use y equals, and then our placeholder for that inner function is u. Okay, so our outer function is going to be y equals u to the 4th, understanding that u represents the inner function. So then our inner function in this problem is going to be u is x squared minus 3x plus 5. And the chain rule says in Leibniz notation that if we want to find the derivative of y with respect to x, then that is going to be the derivative of y with respect to u times the derivative of u with respect to x. For us, that means that for this particular problem, if we're finding the derivative, we differentiate our outer function first at the inner function. So basically, you leave the inner function alone and you just do the work to the outer function. So if our outer function is something being raised to the 4th power, we know that that's just the power rule for polynomials. So we would bring the 4 down in front. We have our inner function here inside our parentheses. I should maybe make that parenthesis a little bigger. And then we always have to subtract 1 from the exponent. So that's the derivative of our outer function. Now, when we say we differentiate the outer function at the inner, that means that you just rewrite the inner right where it is. So x squared minus 3x plus 5. But now we have to multiply by the derivative of the inner function. So now we have to multiply by the derivative of x squared minus 3x plus 5. So again, we're going to be using the power rule for that. The derivative of x squared is going to be 2x. The derivative of negative 3x is going to be negative 3, and the derivative of positive 5 would be 0. So here is my final answer for my derivative. And again, I could write this as dy dx equals, or I could write this as y prime equals. You could rearrange this. You could put the 2x minus 3 right after the 4 and before the trinomial cubed, but it doesn't really matter. The answer is the answer. Let's take a look at letter B. We have y equals e to the x cubed. So again, we have to figure out what is our outer function here And what is our inner function? For this particular problem, our outer function is going to be e to the u power. And our inner function is going to be that exponent, which in this case is u equals x cubed. So we know that our derivative, again, you could call it dy dx, you can call it y prime, it really doesn't matter, but our derivative is going to be equal to the derivative of the outer function. Well, we know that the derivative of e to the u is e to the u, so it's going to be e to the u, but again, u is x cubed. So there's the derivative of my outer function at the inner, times the derivative of the inner function. We'll have to multiply by the derivative of x cubed, which is 3x squared. And then, again, if you wanted to put the 3x squared in front of the e to the x cubed, that's probably how you'd see an answer like this in the back of the book. But this answer is a great answer, just like it is. All right, let's take a look at letter C. Let's try to figure out what is our outer function here and what is our inner function. Well, I think this one's a little bit easier to see. The outer function is y equals sine of something, right? So sine of u. And then our inner function is what's inside the parentheses. U is cosine x. So our derivative, again, dy dx or y prime, doesn't matter, is going to be equal to the derivative of the outer function at the inner. Okay, so what is the derivative of sine? The derivative of sine is cosine. So it's going to be cosine, but it's at the inner, so it's cosine of cosine x, that's kind of weird, right? Times the derivative of the inner function. Well, the inner function is cosine x. What is the derivative of cosine x? That is negative sine x. And then in this case, I probably would take the time, because of that negative sign, to put the negative in front. So I would put negative sine x times cosine of cosine of x. And that's how I would leave my answer for letter C. In example 2, we're changing gears a little bit here. Now we've got a root function with a polynomial function underneath it. So when you use the chain rule on root functions, you definitely want to take the time to rewrite your root function as a power. So when we think about a cube root, remember a cube root is really a 1/3 power. So this function is really y equals 2x cubed plus 3x raised to the 1/3 power. So if I want to differentiate that, now I'm going to think about what is my outer function and what is my inner function. In this case, my outer function is going to be something to the 1/3 power. So y equals u to the 1/3 power. And my inner function is going to be that something that's being raised to the 1/3 power. So u is going to be equal to 2x cubed plus 3x. All right, so now we do exactly what we've been doing. Our derivative, again, call it dy dx, call it y prime, doesn't matter. I like to switch it up back and forth just so that you're always used to both notations. So dy dx is going to be equal to, we first take the derivative of the outer function at the inner. So again, thinking we're differentiating a polynomial using the power rule. Our exponent is 1/3, so that is going to come down in front. Then we have our inner function. We know that's not going to change for this first step. So I can leave that as 2x cubed plus 3x. Now I have to subtract 1 from 1/3. So 1/3 minus 1 is going to give me a new exponent of negative 2/3. And then I have to multiply by the derivative of the inner function. The derivative of 2x cubed plus 3x. I bring the exponent 3 down. It gets multiplied by the 2. So that's going to be 6x, and then the square or the cubed becomes squared, plus the derivative of 3x is just 3. All right, now how do I rewrite my answer? Well, there's a couple things we can do here. First of all, let's think about where things live in terms of our answer. We have a negative exponent, so I know that that 2x cubed plus 3x should probably get moved downstairs because we never want to leave answers with negative exponents. So dy dx is equal to, I'm going to draw a fraction bar here. Now if I've got 1/3, that means that the 3 lives in the bottom. And if I'm bringing that 2x cubed plus 3x to the negative 2/3 power downstairs, the power is going to become positive, but I'm going to rewrite it in its root form. So it's going to be 3 times the cube root of 2x cubed plus 3x squared. Okay, so that takes care of the first part. And then our 6x squared plus 3, that lives upstairs. Now there is one more thing that we could do here, and some of you already may see it, some of you may not, that's okay. 6x squared plus 3, that has a GCF of 3, so if we factored a 3 out, this would become 2x squared plus 1. And the benefit of doing that is we've got this 3 right here and this 3 right here, which we can cancel. So our final answer in its most simplified form, dy dx is equal to 2x squared plus 1 over the cube root of 2x cubed plus 3x quantity squared. Doesn't look very pretty, but that's our derivative. Letter B in example 2 is interesting because this is both a product and it requires chain rule. So this is a common problem that you'll see in calculus, and you'll probably see one of these for sure in the multiple choice section of the AP test. It's something that they always like to put on there, a combination product rule and chain rule problem. So we start by thinking about the chain rule, by thinking about the product rule. And when we do the product rule, remember we're thinking about which function is the first function and which function is the second function, because the product rule is first d second plus second d first. And then as we're doing our product rule, whenever we have to do the derivative of something, that's when the chain rule is going to come in. So my y prime, and this is going to look long, my y prime is going to be equal to, and again, start with the product rule. First is 2x minus 5 cubed. D second. So now I have to take the derivative of x plus 1 quantity to the 5th power. So chain rule, differentiate the outer at the inner. So my outer function is something to the 5th power. So bring down the 5. The inner function stays the same. So it's going to be 5 times x plus 1. And then the exponent becomes a 4. And then I have to multiply by the derivative of the inner function. Well, the derivative of x plus 1 is just 1. Okay, so that's first d second. Now I have to do plus second d first. So second is going to be x plus 1 to the 5th. And then d first. So the derivative of 2x minus 5 quantity cubed, I have to bring the 3 down. The 2x minus 5 stays the same. The exponent becomes a 2. And now I have to multiply by the derivative of the inner function. So the derivative of 2x minus 5 is 2. All right, so that is the first step, just making sure that you do both the product rule and the chain rule correctly. And now we can do a little bit of simplifying. We're not going to go crazy here, but any coefficients should be multiplied together and then moved out in front of a term. And then if you wanted to take out a GCF, you could. So I will show you what I mean. Y prime is going to be equal to, now remember, all of this is your first term and all of that is your second term. So the coefficients that I'm talking about would be the 5 right here and the 1 right here. We multiply those together and we get 5. And then we have 2x minus 5 cubed times x plus 1 to the 4th. And in my second term, I can multiply the 3 times the 2, which gives me 6. And then I have 2x minus 5 squared and x plus 1 to the 5th. Now, in terms of GCF, you know that both of your terms have families of 2x minus 5 and families of x plus 1. So you could simplify further by pulling out those families. So I'm going to put an or here, and I'm going to show you what I mean, just because this might be something that you would see as one of your answer possibilities in the multiple choice portion of an AP test. I can't pull a GCF out of 5 and 6, so those are going to stay where they are. But I can take two families of 2x minus 5 out, and I can take 4 families of x plus 1 out. And so then what I would have left in the first term would be 5 times 2x minus 5. And what I'd have left in the second term would be 6 times x plus 1. And then if you wanted to distribute the 5, distribute the 6, and combine like terms within the bracket, you could. So then this becomes 10x minus 25 plus 6x plus 6. And so y prime would be equal to, and then if I combined like terms here, 10x plus 6x is 16x, and negative 25 plus 6 is negative 19. So my final answer would be 16x minus 19 times 2x minus 5 squared times x plus 1 to the 4th. Okay, that would be the most simplified form that you could give for your answer. However, I want you to know that in terms of quizzes and tests for this class, I am going to be satisfied with an answer that looks like this one back here. So I will let you know in the instructions how far I expect you to go in terms of simplifying. But for a problem where you combine product rule with chain rule, the one that I just circled in purple would be what I would expect your answer to look like. Letter C is a great problem to consider. We are comparing y equals sine squared x versus y equals sine of x squared. They are definitely not the same thing. Now, these both require chain rule, but the inner function and the outer function on these two are different. So let's kind of divide our page in half here and let's look at them individually, and we can see how they are different as we work through the problem. Y equals sine squared x is really y equals sine x being squared. My outer function is going to be something is squared, right? So u squared. And my inner function then is going to be my sine x. U equals sine x. So when I differentiate this, y prime is going to be equal to, again, start with the outer. So bring down the 2. The inner function stays right where it's at. And then my exponent would become a 1. We don't usually write it, but because we're doing chain rule, we're going to write it on this step. And then I have to multiply by the derivative of the inner function, and the derivative of sine x is cos x. So my answer is y prime is 2 sine x times cos x. That is the derivative of sine squared x. All right, now sine of x squared, that's different, because now my outer function is just y equals sine of u. And my inner function is u equals x squared. So this time when I do the differentiating, y prime, I have to start with my outer. The derivative of sine is cosine, so I'm going to have cosine of my inner stays, so it's cosine of x squared, times, then I have to multiply by the derivative of x squared, which is 2x. So this time my y prime is going to be equal to 2x cosine of x squared. Our last example today gives us an exponential function with a base that is not e. And we did explore this a little bit earlier, but there's a very important box right here that you might want to highlight. The derivative of an exponential function when your base is not e is going to be whatever your function was. A is a base, right? And it can be e, but we think of it this way when it's not e. Some base to the x power is equal to the function itself times the natural log of the base. Well, when your base is e, the natural log of e is just 1. So that's why the derivative of e to the x is e to the x. So it does follow this rule, but we just think of that as a special case of a derivative of an exponential function. So in this case, we have an exponential function, but we also have chain rule because our outer function is y equals 3 to the u. And so again, here's our exponential function that we're going to need that rule for. And then our inner function is u is equal to 2 over x, which you should be thinking is really a polynomial. 2 over x is really 2 times x to the negative 1 power. So when I take my derivative, my dy dx, or my y prime, however you want to write it, let's start by differentiating the outer function at the inner. So we know that the derivative of 3 to the u is going to be 3 to the u, so in this case 3 to the 2 over x, times the natural log of the base, so times natural log 3. But now I have to multiply times the derivative of the inner function. And the derivative of 2x to the negative 1, that's going to be a power rule problem. So I bring down the negative 1 and multiply it by the 2. So that's going to give me negative 2x. And then I have to subtract 1 from my exponent. So negative 2x to the negative 2 power. And of course, I should probably clean this up a little bit for my final answer. So my dy dx is going to be equal to, I'm going to put the negative 2 in front. So negative 2. I'm going to put my ln 3 next. And then I've got my 3 to the 2 over x. And then downstairs, that x to the negative 2 comes downstairs and becomes x squared in my denominator. So this is how I would write my final answer for my final example of this set of notes.